Tonight, let's stay with one calm question. Why doesn't time flow the same everywhere? Not in a poetic way, in a physical way. Because most of us grow up believing time is a single river, the same for everyone, the same in every room, the same on every street, the same on every planet. 1 minute is 1 minute, 1 hour is 1 hour. But the universe doesn't treat time like a single river. It treats time like something that can stretch and compress, depending on where you are and how you move. And once you see that, you can't fully unsee it. So in this episode, we will explore time dilation. Slowly, clearly, without hype, just the real science, told gently. And by the end, you'll understand something quietly surprising. Time is not a single clock, shared by the universe. Time is something each path carries, like a private rhythm. Let's begin in the simplest way, with a promise your brain likes, a promise of order. Imagine you and I are holding identical clocks, built in the same factory, set to the same second. We place them side by side, and they tick together perfectly. Tick, tick, tick. In your everyday life, this is how time feels, a shared beat. But the deeper question is, what if we separate those clocks and bring them back later? Will they still agree? Your intuition says yes. Physics says not always. And the difference is not philosophical, it's measurable. Before we go to space or fast travel or extreme gravity, let's build the foundation the way science did. Let's start with what time is, in the language physics uses. In physics, time is not only a feeling. Time is part of the coordinate system we use to describe events. An event is something that happens, a flash, a collision, a heartbeat, a satellite signal. To describe an event, you specify where it happened and when it happened. So time becomes part of the map of reality. And here is the first quiet shift. In classical thinking, space is one thing, time is another. Space can stretch, time is fixed. But in modern physics, space and time are woven together. Not as a metaphor, as a structure. We call it space-time. Now, space-time can sound intimidating, so let's make it feel calm. Imagine a stage. On this stage, every event has an address, 3 numbers for space and 1 number for time. And if you and I agree on the stage, we think we agree on the order. But then physics asks, what if your stage and my stage are not aligned? What if motion changes the angle of how we slice reality into space and time? That is the core of relativity. It's not that time becomes unreal, it's that time becomes connected to the observer. Now here is something important. Relativity does not say everything is subjective, nothing is real. Relativity is the opposite. It says there is a deeper structure, and that structure is consistent. Even if different observers describe it differently, like 2 people using different maps to describe the same terrain. So, why doesn't time flow the same everywhere? There are 2 main reasons: speed and gravity. Speed causes time dilation, special relativity. Gravity causes time dilation, general relativity. Tonight we will build both, in a way that stays gentle. And we'll keep asking one guiding question. If time can change, how do we know? How do we measure it? And why should you care? Let's start with speed, special relativity. It begins with a simple, stubborn fact: the speed of light. In a vacuum, light travels at a constant speed, and it does not care how fast the source is moving. That sounds simple until you feel what it implies. Because in everyday life, velocities add. If you walk forward on a moving train, your speed relative to the ground is train speed plus walking speed. But light does not behave like that. If a flashlight is turned on inside a moving spaceship, the light still moves at the same speed, as measured by an outside observer. So if speeds don't add normally for light, something else must adjust. And the universe chooses time and space. Now let's make this feel intuitive. Imagine a clock that measures time using light, a simple thought clock. A beam of light bounces between two mirrors. Up, down, up, down. Each bounce is a tick. Now imagine this clock is floating in space, and you are watching it. If the clock is not moving relative to you, the light travels straight up and down, a neat path. But if the clock is moving sideways while the light bounces, then from your perspective, the light travels a longer diagonal path because the mirrors are moving sideways as the light travels. Longer path, same speed of light. So what must happen? The tick takes longer, which means the moving clock ticks slower. Not because it is broken, but because the geometry of space-time demands it. This is time dilation due to speed. Let that sink in. If motion causes the light clock tick to slow, then motion causes time itself for that moving system to pass differently relative to you. And this is not only for light clocks, it applies to any physical process. Atomic vibrations, chemical reactions, biological processes, everything that can act as a clock. Because the underlying rule is not about gears, it is about space-time. Now you might ask, if moving clocks run slow, why don't we notice? Because in everyday life, our speeds are tiny compared to the speed of light, so the effect is extremely small. But small is not the same as zero, and the universe is patient and precise. Now let's create a calm example. Two twins, one stays on Earth, one travels in a spaceship. This story is famous, and it's often told dramatically, but we will tell it quietly. The traveling twin moves at very high speed, near the speed of light, for a long time, then returns. From the perspective of the Earth twin, the traveler's time runs slower because of speed. So the traveler returns younger, not by magic, by geometry. Now, the full twin paradox has nuance about acceleration and changing frames, but the core idea remains. High speed changes how much time accumulates along a path. This word matters. Accumulates. In relativity, time is not only a flow, it is something like a length along a path in space-time. We call it proper time. Proper time is the time measured by a clock moving along with you. It's the time your body experiences. So the universe is not asking, what is the one true time? It's asking, how much time passes along each world line? World line is just a name for your path through space-time. Now here is a small wow moment. In relativity, different paths between the same two events can have different amounts of proper time. That means time is not only about where you start and end, it's about how you travel. The route matters, and that is deeply physical. Now, before we go to gravity, let's make speed dilation feel even more real. Because if you've never seen it, it can still feel abstract. So let's bring in something practical. Satellites, GPS, your phone. GPS works because satellites carry atomic clocks, and those clocks must stay synchronized with clocks on Earth. But satellites move fast, and they are also higher in Earth's gravitational field, so their time shifts. If engineers ignored relativity, GPS errors would grow rapidly, and your location would drift. So relativity is not optional. It's not a theory living in a book. It is part of the way our world functions, right now. So speed changes time. Now let's go to gravity, general relativity. And here is the guiding picture. Gravity is not a force pulling you through space. Gravity is the curvature of space-time. Mass and energy shape the geometry, and objects follow the geometry. Now let's make that calm. Imagine space-time as a kind of fabric. Not literal fabric, but a way to visualize curvature. A massive object like Earth changes the shape. And when the shape changes, paths change. Objects fall not because of a pulling string, but because straight lines in curved space-time look like curves in space. Now the key question, if gravity is geometry, what happens to time? The answer is, gravity affects time directly. time runs slower in stronger gravity. The closer you are to a massive object, the slower your clock runs, relative to a clock farther away. This can sound impossible, so let's build intuition. Here is a calm way to hold it. In general relativity, time is part of space-time, so if space-time is curved, time is curved too. And curvature can change the rate at which clocks tick. Again, not because clocks break, but because the structure they live in is different. Now let's go slowly. Imagine two identical clocks. One is on the ground. One is on a mountain. Which one ticks faster? The one higher up ticks slightly faster. Because it is farther from Earth's mass, so gravity is slightly weaker, so time dilation is slightly less. The difference is tiny, but real, and measured. Here is the second wow moment. Time is not only slowed by speed, time is also slowed by gravity. And those two effects can compete. A satellite is moving fast, which slows its time, but it is higher up, which speeds its time relative to the surface because gravity is weaker. So engineers must account for both. Now let's pause and ask something deeper. Why does gravity slow time? There are different ways to explain it. One common intuitive explanation is this. Light climbing out of gravity loses energy, and its frequency shifts. That is gravitational redshift. If light's frequency changes, then processes tied to that frequency change too. So time itself, measured by oscillations, shifts. Another explanation is geometry. In curved spacetime, the spacing of time coordinates changes with gravitational potential. So a second near a massive object is not the same slice of spacetime as a second far away. But the most important point is, it is a consistent rule, not a trick. Now let's make gravity time dilation feel personal. When you stand on Earth, your head is slightly higher than your feet. So time at your head runs slightly faster than time at your feet. The effect is unbelievably small, but in principle, you are not one perfectly synchronized object. You are a stack of tiny time differences. And you don't notice because biology is not that sensitive, and the difference is so small. But the universe is doing it anyway, quietly. Now, imagine the effect near a black hole. Near a black hole, gravity is intense. Time dilation becomes dramatic. From far away, an object falling toward the black hole appears to slow down, as if time is stretching, while for the falling object, its own time feels normal. This leads to some of the strangest images in physics, and they are not science fiction. They are consequences of equations. But we will keep this gentle. The lesson is, gravity can reshape time strongly. Now you might wonder, does that mean time travel is possible? Careful. Time dilation is not the same as traveling to the past. Time dilation allows a kind of travel to the future, in the sense that if you experience less time than others, you can arrive at a future where more time has passed for them. That is a real effect, but it is not a machine that sends you backward. So it is a quiet kind of time travel, one way, forward. Now here is something else important. People often think relativity says everything is relative, so nothing can be agreed on. But relativity gives you something you can agree on: the space-time interval, proper time. These are invariants. Even if observers disagree on space and time separately, they can agree on the combined structure. So the universe has deep consistency. Now let's put the whole idea into a calm mental model. You can think of time like this, not as a global river, but as a local rhythm. Each clock carries its own rhythm, depending on its motion and gravity. And when clocks meet again, they compare. The comparison is not an argument, it's a measurement, and the differences tell you about space-time. Now let's make this episode truly useful. If you want to be able to explain time dilation to someone in a simple and trustworthy way, you can use 3 sentences. 1. The speed of light is constant. 2. So moving clocks must tick differently to keep that constant true. 3. Gravity is curved space-time, and curvature changes how time accumulates. That is the skeleton. Everything else is detail and beauty. Now let's add beauty. Not poetic beauty, scientific beauty. We will explore several gentle thought experiments, and each will add clarity. Thought experiment 1. The train and the lightning. A classic. Imagine a long train moving fast, and lightning strikes both ends of the train. For an observer standing on the ground, the strikes might be simultaneous. But for an observer on the train, moving toward one strike and away from the other, the light from the strikes reaches them at different times. So they may conclude the strikes were not simultaneous. This introduces another deep concept. Simultaneity is relative. That means the universe does not provide a universal now. There is no single slice of the cosmos that everyone agrees is the present. This is not philosophy. It is physics. And it's part of why time feels less absolute in relativity. Now, if simultaneity is relative, then time itself cannot be universal, because time is built from ordering events. So relativity changes the structure of what we mean by time. Thought experiment 2. The light clock again, but with numbers. If the light must travel a longer diagonal path, and the speed is fixed, then the time between ticks increases. It is geometry, and geometry is dependable. This is why physicists trust it. Thought experiment 3. The mountain clock. A clock at higher altitude runs slightly faster. Now imagine two identical twins. One lives at sea level, one lives in a high-rise apartment for decades. At the end, the high-rise twin has experienced slightly more time. The difference would be tiny, but measurable with precise clocks. So gravity makes your location matter. Now, you might ask, if time changes with speed and gravity, why does the universe allow time at all? Why not keep everything simple? Because time is not a separate ingredient. It is part of the structure that makes causality work. Space-time provides the rules for what can influence what can cause what. And relativity is deeply connected to causality, to the speed limit set by light. So time dilation is not a glitch. It is part of the mechanism that keeps the universe consistent. Now, let's address a subtle feeling many people have. If time is not universal, does that mean my experience of time is an illusion? No. Your experience of time is real. It is your proper time, your local rhythm, your sequence of moments. Relativity does not erase experience. It describes how experiences compare across different conditions. And that comparison is the science. Now, to make this even more grounded, let's talk about what a clock is. In physics, a clock is any periodic process, a swinging pendulum, a vibrating atom, a rotating planet. If time dilation is real, it should affect all clocks because it affects the underlying structure that makes processes unfold. And experiments confirm that. Atomic clocks, the most precise clocks we have, show time dilation exactly as predicted. So time dilation is not about machinery. It is about reality. Now, there is a gentle paradox here. From your own perspective, your time always feels normal. Your heartbeat feels normal. Your breath feels normal. Your thoughts feel normal. Time dilation does not feel like slow motion to you. It is only visible when you compare with another clock that took a different path. This is why relativity feels slippery, because it hides inside comparisons. But that also makes it elegant, because it is not about feeling, it is about structure. Now, let's do a calm and vivid scenario. Imagine you could travel at 90% of the speed of light for what feels like 1 year. From Earth's perspective, more than 1 year would pass. Depending on your exact speed, maybe several years. You return, and Earth has aged more. You are not a superhero. You are just on a different path. And this is the simplest sense in which relativity gives you the future. Not by breaking rules, but by following them. Now, let's deepen the gravity side again. Because gravity time dilation often surprises people more than speed. Speed dilation feels like motion affects measurement. Gravity dilation feels like space itself affects time. But gravity is space and time together. Here is another calm explanation. In general relativity, gravity affects the rate at which time passes, because time is part of the metric. The metric is the thing that tells you how to measure distances in space-time. In a gravitational field, the metric changes, so the conversion between coordinate time and proper time changes, which means clocks tick at different rates depending on gravitational potential. That is the technical core. But you don't need the equations to feel the meaning. It means time is not evenly distributed across the universe. It is shaped by mass. Now, this leads to a quietly haunting idea. The universe is not synchronized. There is no cosmic master clock. Different regions, different conditions, different rhythms. And yet, the universe remains consistent because physics provides the translation rules. Relativity is the translation layer. Now let's do another gentle thought experiment. Imagine a planet much more massive than Earth, but with a surface you can stand on. If you lived there, your clocks would run slower relative to faraway space. If you could communicate with someone far away, their time would appear to move faster, and yours slower. Not because of emotion, because of gravity. This is real. Now, to keep this episode calm, let's place a soft boundary. We will not chase the most extreme cases too hard. We will focus on understanding. Understanding is the calming part, because confusion is what makes the mind restless, and clarity is what makes the mind settle. So now, we will do a slow recap. Time dilation comes in two forms. Speed. Moving clocks run slow, relative to an observer, because the speed of light is constant. Gravity. Clocks run slower closer to mass, because space-time is curved. In both cases, your own time feels normal, and differences appear only in comparisons. Now, let's answer the original question more directly. Why doesn't time flow the same everywhere? Because time is not a universal substance. Time is a measurement of how processes unfold, and processes unfold within space-time. And space-time has geometry. Geometry depends on motion and mass. So time depends on motion and mass. That is the quiet truth. Now, there is one more layer we can add, a layer that makes it even more satisfying. The idea that time is linked to energy. In general relativity, mass energy tells space-time how to curve. So energy density affects time. This means the universe ties together the physical content of reality and the rate of time. So time is not independent. Time is woven into the same fabric as energy and geometry. This is why in extreme environments, like near neutron stars or black holes, time behaves dramatically, because energy density is dramatic. Now, let's shift into a more story-like explanation, still scientific. Imagine you live in a city, and every neighborhood has its own pace. Some neighborhoods walk slowly, some move quickly. But it's not about personality, it's about the terrain. Up a steep hill, you move differently than on a flat road. In the universe, gravity is that terrain. Motion is that terrain. So time becomes a pace that depends on the path. Now, you might wonder, if time is not universal, does that affect cause and effect? Yes, and relativity protects cause and effect. One of the deepest features of relativity is that it preserves causality. Nothing can send information faster than light in normal conditions. This keeps the structure of cause and effect consistent, even though time is not universal. So relativity is not chaos, it's a careful design. Now, we should address a common misunderstanding. People sometimes say, time is an illusion. That can be a philosophical statement, but physics doesn't need that language. Physics says, time is part of the coordinate system and part of what we measure. It behaves in specific ways, and those ways are confirmed. So instead of saying time is an illusion, a safer statement is, time is not absolute. Time is relational. Time depends on the frame and on gravity, but it remains measurable and real in that sense. Now, let's introduce one more calm concept: reference frames. A reference frame is just a way of describing motion. If you are sitting in a moving train, you can choose a frame where you are at rest and the world moves. Physics allows that. But when you compare two frames moving relative to each other, time can differ. Relativity gives the precise rules. So the point is not which frame is correct. The point is how they relate. Now, to make this feel natural, let's do a daily life analogy. You and a friend watch the same movie, but on different devices. One device is set to play at normal speed, the other slightly slower. You start at the same moment, but after an hour, you are out of sync. Now the movie is the same, the content is the same, but the playback rate differs. This is not exactly time dilation, but it gives your mind an image. Different systems, different rates. Then comparison reveals the difference. Now, here is the third wow moment. The universe has built-in time differences, even inside technology we rely on. GPS satellites. They are living relativity machines. Their clocks must be corrected because they are moving fast and living higher in gravity. If you want a modern civilization, you include time dilation. So time dilation is not exotic, it is quietly everywhere. Now, let's go even deeper, but still gently. We will discuss what time is in the context of thermodynamics, because sometimes people ask, if time is relative, why does time have a direction? Why do we remember the past, not the future? This is often called the arrow of time. Relativity describes how time measures differ, but it does not by itself explain why time feels like it has a direction. That comes from entropy, from the statistical tendency of systems to move toward more probable states. So there are two aspects of time: the relativistic structure, how time intervals compare, and the thermodynamic arrow, why we experience time moving forward. Both are real parts of physics, but tonight, we won't chase entropy too far. We'll just notice, even the direction of time is connected to physical laws, not to human opinion. So the universe is deeply structured. Now, let's bring the focus back to the listener. If you are listening late at night, maybe your mind is busy. Time can feel heavy, like it is pressing, like tomorrow is approaching too quickly. Relativity offers a strange comfort. It reminds you that time is not one hard wall. It is flexible and woven. And while we can't control it the way stories suggest, we can at least understand it. Understanding is calming, because understanding turns fear into form. Now, let's walk through a few more examples, slowly. Example 1. Airplanes. Atomic clocks flown on airplanes, and compared to clocks on the ground, show tiny differences. Because the airplane is moving and also experiencing slightly different gravity. The difference is small, but measurable. This is not science fiction. It has been tested. Example 2. Tall buildings. Clocks at the top of a tall building tick slightly faster than clocks at the bottom. Again, tiny, but measurable. Time is literally not the same on different floors. Example 3. Astronauts. Astronauts experience time differently than people on Earth because of speed and gravity differences. It's not dramatic, but it is real. Now, you might ask, if time differs, can we use it? Can we engineer time differences? In principle, yes, but practically, it is extremely difficult to make large effects. To make dramatic time dilation, you need enormous speeds, or enormous gravity. and both are far beyond normal human experience. So relativity is real, but it is not a convenient tool. It is a truth we live inside. Now, let's address one more delicate point. People sometimes worry, if time depends on motion and gravity, what is happening right now in the universe? What is the present? Relativity suggests there is no single present across all space. Different observers can slice space-time into now slices differently. So the universe is not organized into universal moments. It is organized into events and the relations between them. This can feel unsettling, but it can also feel freeing, because it means the universe is not forcing one timeline on to everything. It is allowing a richer structure. Now, if that feels too abstract, here is a calmer way to hold it. For your life, your proper time is what matters. Your day, your night, your heartbeat. Relativity is not taking that away. It simply says, when you compare your time to another path, the comparison depends on motion and gravity. So you can keep your everyday time and still accept the deeper truth. Now, let's do a long, gentle recap, because repetition is calming. Speed time dilation. Moving clocks run slow relative to you. Gravity time dilation. Clocks deeper in gravity run slow relative to you. In both cases, your own time feels normal, and differences are revealed when clocks reunite or communicate. Time is not a single universal river. It is a path-dependent quantity. And this is not just theory. It is used in GPS and confirmed by experiments. Now we will move toward a soft landing. But before we do, let's give your mind a final, satisfying picture. Imagine space-time as a landscape. Some parts are flat, some are steep. Motion is like taking a longer route in a way you can't see. Gravity is like walking in a valley, where the landscape shapes your pace. Each path has its own length, its own accumulation of time. And when two paths meet again, the clocks compare like travelers who took different roads. Neither traveler is wrong. They simply experienced different lengths of journey. That is time dilation. Now let's end with one gentle thought. Time feels like pressure when we don't understand it. But time becomes quieter when we do. Because the universe is not rushing you. The universe is simply structured. And your mind, even when it can't sleep, can find comfort in structure. So tonight, if you remember one sentence, let it be this. Time does not flow the same everywhere, because time is part of space-time, and space-time depends on motion and gravity. In the next episode, we'll explore another question, just as calmly. If you could move near the speed of light, what would Earth look like when you returned? For now, let your thoughts slow. Let the idea settle. Time is not a single river. It is a quiet geometry.